So in this case study, we're going to look at modeling as a way to account for variability. We're going to use the Indian cattle data to really dig into this. And I think this is the first time in this course that we've come across this data. It was used quite a bit in the other course on an introduction to working with data. And there's more details given in topic 1, where you can get the data and some background relating to this case study. But as a brief overview, this case study is a survey in Bengaluru, which is a major Indian city which has experienced fast urban growth. One aim of this case study is to investigate the effect of the urbanization on dairy production. So in this case study, we look at variables that account for variability in the average milk production per cow variable. So there's lots of different variables which were gathered throughout this survey, and this is just one of those many variables where the different farmers were asked, what is the average milk production that you get per cow? So first, we're just going to go back a step, and we'll just have a little recap on accounting for variability. So imagine that we have a bunch of data about milk production from different cows. Sometimes you might notice that the amount of milk one cow produces is different to another. We want to understand why this happens. This understanding is important because it helps us to figure out what factors really affect how much milk a cow gives. By getting this, the farmers can then consequently know how they can optimize their kind of dairy farming, if that is what they're interested in. So to do this, we use different pieces of information, which we're going to call variables, from our data to see how they relate to the milk production. These variables help us to account for those ups and downs and those fluctuations in milk production. An ANOVA is one way to account for variability in the data. Under resources or additional slides on interpreting and using an ANOVA, just to help with a refresh on the topic. We also went through it back in topic 1, but this was covered quite a bit in an introduction to working with data. There are also those questions that were from the previous course that are also available at the end of this topic, just if you wanted to go over them again to refresh and remind yourself, familiarize yourself. Anyway, so for this study, what is our aim? Our aim is, so this case study example looks at variables that account for variability in the average milk production per cow variable. The ultimate goal here is to make sense of why some cows produce more milk than others. And once we figure that out, we can make some important conclusions based on our study, which can be very useful for various purposes. So we're going to look at 2 different parts in this case study example. And we're going to look at these about 12 variables, I think that is. But there are a lot of variables in the data. We've just taken these 12 from the data to illustrate our point. And just note that all of this is for illustrative purposes, and that this wasn't, there may be some variables in that data which really help account for this variability in the outcome. But let's get our ANOVA table. So we first account for the variability in the outcome through an ANOVA table. And here's our ANOVA table. We've got our 12 variables in there. There's more information, as I said, on interpreting the ANOVA table back in or over in slides at the bottom of this topic, if you wanted to familiarize yourself. But here's our ANOVA table. And we can see here of how kind of how much variability each of these variables account for in this outcome. So as a little reminder, ANOVA splits the overall variation into 2 components: the variation due to differences in means, which is for our 12 variables, the kind of variation that they account for, and the residual variation, which is your variation, your leftover, the rest of it, the stuff that we've not accounted for. As said, there's these guides under resources where we can go through them. So the first column gives a corresponding variable that the rows gives the details for. We get between different treatments difference for the variables. For example, the first row will give the difference between the factor levels in the health troubles variable. So if we just look at this first row here, we see that 16.90, it accounts for 16.90 amount of that variability out of a possible 3,173. For the residuals, we then get the leftover error that's not accounted for. And so just as a little reminder, this is our degrees of freedom. These are our sums of squares, our mean sums of squares, which is the kind of sums of squares per degree of freedom, and then the F value, which is the proportion of variability that variable accounts for compared to the residuals. So here's this 16.9 over this 700 over this 11.98. Sorry. So overall, if we look at this entire thing, then we can add up all of our sums of squares values for our 12 variables, or we do 1 minus this one. It's the same number. But overall, approximately 30% of variation is accounted for in this ANOVA table. We now look at an analysis of deviance table, which is a very similar type table, and this is just another way that we can account for variability in the outcome. Again, while analysis of deviance wasn't covered on the Introduction to Working with Data course, there is at the bottom of this page some information on interpreting an analysis of deviance table, which I recommend you have a go through to help just understand what's going on here, as well as lots of different questions, similar questions to the ones like on ANOVA, on interpreting the ANOVA and on filling in the ANOVA, but this time for an analysis of deviance, just to really help get to grips with things. So we've got these 5 different variables. So variable is 5 different columns, variable being our variable, degree of freedom, or DF being our degree of freedom. Then we have our deviance. This is the variability that the variable accounts for. So health troubles accounts for 0.3 deviance, whatever that may mean, which we'll kind of get to in a second. We have our residuals degrees of freedom. So this is our kind of leftover degrees of freedom now. So how this table works a little bit more, and this is given in more detail in the guides. But if we look at our first row, this is if there's no variables in the model at all. And so this is kind of like our total. So overall, there's 200 degrees of freedom, which is exactly the same number of degrees of freedom we had before in our total, which makes sense because this is just going to be your number of rows minus 1 in both cases. And there's 67.89 residual deviance. That's, again, residual deviance is here the kind of leftover or residual deviance. So kind of deviance being your kind of departures from your model. And so our kind of total residual deviance, as it were, is 67.89 if there's nothing in the model. When we then add in health troubles, there's a deviance of 0.3. So our residual deviance, our leftover deviance, is now 67.59, which is just basically the difference. So 67.89, our top one, minus our 0.3 deviance that health troubles accounts for, gives us our 67.59. Similarly, with our residual degrees of freedom, we had 200 at the start. We then minus our 1, because this column, this row here now says if we had health troubles in the model, which gives us 199 degrees of freedom, because we've done 200 minus 1. And as we go down, we start minusing more and more because we start adding more and more variables to our model. And so our residual deviance and our residual degrees of freedom decreases because we're adding more to our model. Now, this measure of variability says that roughly 23% of variability in the outcome variable is accounted for from these variables. So we've got these ANOVAs and we've got this analysis of deviance. Our ANOVA said roughly 30% of variability in the outcome variable is accounted for from these variables. Our analysis of deviance said that the model with these variables in it accounts for roughly 23% of variability in the outcome variable. And so we can see that there's some similarities between these two measures of variability, and that's all that these are. ANOVA and analysis of deviance are just different measures of variability. Both of these measures of variability agree that transect accounts for the most variability, settlement the second most, and N-hours the third most. They also agree that DPS, number of cows, own production, and N-mills account for very little variability. So if we just have a quick look back on it with transect, we see here that transect accounts for 6.04, which is our largest amount of deviance that anything accounts for here. We can then see that settlement accounts for 3.79, which is our second largest on here. And then we see that hours for pasturing is 1.43, which is our third largest of our deviances. When we go back to our ANOVA, we see that, again, transect accounts for the most at 382.57, followed by settlement at 245.16, followed by hours for pasturing at 81.13. So both, there are similarities there between our two measures of variability, where they're both agreeing on kind of things that are accounting for a lot of that variability and things that aren't accounting for as much. And in the middle, there's some murkiness, but just in terms of accounting for that variability, both tools are actually very similar. So ANOVA and analysis of deviance are both measures of variability. They give the same sort of results in terms of understanding variability in the model. Here we have two examples, but there's many other ways to account for variability as well, such as Bayesian methods. And in all cases, all what they're doing is just measuring the variability. Thank you.